Here we have the p-series test, very similar to improper integrals. Back in chapter 8, we had our functions like 1 over x squared going from 1 to infinity. If you recall, we said that this would converge because that my exponent here, it was greater than 1. Okay? If the power of my x was equal to 1, or if it was less than 1, then it would diverge. Well, in the p-series test for our infinite series here, we have the exact same two rules. We have when p is greater than 1, it converges, and if p is less than or equal to 1, it diverges. So this series here is called the harmonic series, and you can read below the origin of it being called the harmonic series. But it's in the form of 1 over n. 1 over n to the p, where p is a 1. Therefore, by the rule, this harmonic series diverges. Okay? But we also have something called the alternating harmonic series. And since we have negative 1 to the n from, or n plus 1, let's say even, from n equals 1 to infinity of 1 over n, this would be the similar series as the harmonic series, except that the terms would alternate. We would get a 1, and then we get a half with a minus, and then we get a third, and then we get a negative quarter, and so on. And since these terms are decreasing, right, in magnitude and approaching 0, okay, and they are alternating, then this series converges. So the standard harmonic series diverges, but the alternating version of it converges. In this example, we're looking at which of the following series converge. Well, we can see this is the harmonic one. This is the one we just talked about. The harmonic series definitely diverges. So we're going to throw that one out. 1 over n squared is just in the form of 1 over n to the p, where p is equal to 2. And obviously 2 is greater than 1, and based on our rule, it converges. So we're good here, right? The third one is in the form of 1 over the square root of n, where we have 1 over n to the 1/2. So if it was just 1 over n to the 1/2, it would diverge because my p here is less than 1. However, we also have the extra bonus here, is that it's alternating. Okay? So since it's alternating, and the terms would go towards 0 and decrease in magnitude, it will converge. So our last one also converges, but without the alternation piece, it would have diverged. But it does converge because of its alternation. 3 more examples for the p-series. 2 of these are p-series and 1 is not. Again, here's the harmonic one, and it's not the alternating version, so this is going to diverge. So we'll say that's wrong because we're looking for which ones converge. This first one, remember the nth term test for divergence says if the limit of your series, your nth term, does not approach 0 as you go towards infinity, then the series will diverge. Well, this is a line over line with leading ratio coefficients of being 1 over 1. So the limit of the nth term is 1. So by the nth term test, this one diverges. Now the one in the middle here, number 2, if you write the over n as 1 over n, and then you have cosine of n pi. This piece right here is the harmonic series. However, this little cosine of n pi would go between cosine of pi to cosine 2 pi, cosine 3 pi, cosine 4 pi. So it does alternate between -1 and +1. Therefore, this is the alternating harmonic series, so it converges. So number 2 does converge. Now we have the ratio test. The ratio test is best used for exponential functions and factorials. The rules are here. If you look at the nth plus first term, divide by the nth term, and you get a limit as you go to infinity being less than 1, it converges. Greater than 1, it diverges. If it's equal to 1, then the test is inconclusive. So the ratio test is best not used when you have a polynomial compared to a polynomial. So if your nth term is a poly over a poly, you're most likely, or you probably will for sure, get this. So let's just show you that example real quick. Okay, so let's say we have this series, and it's in the form of n plus 2 over n squared. These terms would approach 0. Whoops, not a limit yet. And we're going to go from n equals 1 to infinity. So the values would go to 0. So we can't use the nth term test. So we're going to try the ratio test. The ratio test says we're going to take out every n and replace with n plus 1. So this first one's going to read n plus 1 plus 2 for the numerator, but we can call that just n plus 3. So n plus 1 plus 2 is n plus 3. So we n plus 3, and we're dividing that by n plus 1 squared. And that's my nth plus first term. That represents this piece right here. Okay, now we're going to be looking at dividing by the nth term, which is the original function, n plus 2 over n squared. Now we know mathematically we can just multiply by the reciprocal instead of division. So we're going to be looking at the limit of n plus 3 over n plus 1 squared multiplied by n squared over n plus 2. And this is the expression that I'm going to be finding the limit as n approaches infinity. Now if you notice, the numerator is just a cubic, and the bottom is also a cubic, but we're not going to actually expand it. We're just going to recognize they're both cubics. And if you think about expanding, you would have a leading coefficient of 1 on top and a leading coefficient of 1 on the bottom. And that's how you find when n approaches infinity, when you have equal powers, you look at the ratio leading coefficients. So you get 1 over 1, which is 1. So again, we have a problem that makes us not be happy here, because we just did all that work and we got an inconclusive because we got a 1. So if you only have polynomial expressions in your problem, you're best not to use the ratio test. You're hoping for an exponential function or a factorial. Let's show you the next example using an exponential. So the ratio test, I'm going to take 3 to the n plus 1, divide that by n plus 1 squared. And instead of showing the division step, we're going to multiply by the reciprocal automatically, n squared over 3 to the n. Now exponentials in the ratio test can be cleaned up. We're dividing like bases. So when you divide like bases, you subtract exponents. So n plus 1 minus n is just 1. So this leaves me at 3. So what we're doing is we're looking at a limit of 3n squared, which is a quad, over n plus 1 squared, which is a quad. Both of these are quads, therefore we can look at the ratio leading coefficients, which is 3 over 1, which then the ratio is 3, and then by the rule, this series diverges because that has a limit that's more than 1. Now we have an exponential and a factorial. So straight into it, we're going to have 2 to the n plus 1 divided by n plus 1 factorial. And I'm going to multiply that by the reciprocal n factorial over 2 to the n. Like the last example, this 2 to the n and 2 to the n plus 1 do reduce down to the number 2. And n factorial and n plus 1 factorial also reduce down to n plus 1. Let me show you why. Let's say n was 4, right? And then n plus 1 would be 5. And then 4 factorial divided by 5 factorial, where 5 factorial can be written as 5 times 4 factorial. The 4 factorials cancel and you just get the number 5. Now remember, 5 was acting like my n plus 1, right? So that's why we were able to write this as n plus 1. So now we're allowed to apply the limit to our reduced expression. And as our n approaches infinity, the 2 stays 2, the bottom grows without bound, and this ends up being a limit of 0. And 0 is definitely less than 1, therefore this series converges. I'll give you one last example. Let's say we have n factorial on top times n plus 2, and this is being divided by like 4 to the n, and we're going from n equals 1 to infinity. Well, since it has exponentials and factorials in the problem, the ratio test probably is going to be definitely useful. So let's replace the n with n plus 1 factorial. Replace my n plus 2 with n plus 1 plus 2, or n plus 3. And my denominator is going to be 4 to the n plus 1. That's going to be multiplied by the reciprocal 4 to the n, divided by n factorial, also n plus 2 on the bottom. And then we have some cleanup before we apply the limit. My 4 to the n and 4 to the n plus 1 leave a 4 on the bottom. And my n factorial and my n plus 1 leave me an n plus 1 on the top. So I'm looking at a limit of n plus 1 times n plus 3, which is a quadratic. Denominators have a 4 times n plus 2. So in this case, my numerator has a higher power, and we know if my numerator has a higher power, then it's either going to go to infinity or negative infinity. This does go to infinity. So infinity definitely is what? Greater than 1. Therefore, this series diverges.